Okay, this next problem is really just a problem that we worked out in class. It's not a specific sample problem, but through examination of carbon-14 decay and thinking about what it means when we undergo a half-life, we basically can derive at one of the standard equations that we've used. And the standard equation that we're going to use is that the half-life is equal to 0.693 over K. But what I want to do is show you how we can actually derive that equation. And equation derivation is kind of an important skill to be able to think about because it's going to allow us to interconvert different equations. So as this says here, the main equation we use for half-life decay, okay, is shown here. The natural log of how much you have at time t over how much you started with is equal to minus kt. This is actually a little bit different from one we've seen before, which is the natural log of what you have with you start, what you have over at time t equals the rate constant times how much time has passed. So when we invert these two terms, then we get rid of that minus sign. But again, these are equivalent equations. I'll continue this problem by working through this one because that's the one that we used in class. So when considering half-life problems, we can say that when the time equals a special time, t1/2, a time when we've reached the half-life, the amount that we're going to have at that time, which is going to be the amount at time t, will equal half of what we started with. So what we really can say there is when time equals our half-life, the amount that we're going to have is equal to 1/2 what we started with. What this really means is that we can substitute this in this equation. So let's go ahead and do that. And so we'll say the natural log of 1/2 of what we started with over what we started with equals minus k times a special time, t1/2. These can cancel out, so we're left with a natural log of 0.5 equals minus k times t1/2. If we solve for t1/2, t1/2 equals minus the ln of 1/2 or 0.5 over k, and that equals 0.693 over k. So again, not a really involved problem. We didn't really learn anything specifically in terms of application to problems, but it allowed us to say, you know what, we can actually derive the second equation that's important for this chapter when we consider our standard equation applied to the specific time when we have one half-life having passed.